to part 3 of chapter 5. Today we are going to talk about periodic trends, and we're going to wrap up our talk on electrons in atoms. So thus far we've talked a little bit about Bohr models, and the Bohr model was a change in the model from Rutherford. Right? Rutherford's was the planetary model, and it said that there were protons and neutrons in the center of the atom, and then the electrons were orbiting around the nucleus, like planets orbit around the sun. Well, the Bohr model changed that, right? And he put those electrons in energy levels. So now we're going to look at drawing some simple Bohr models, just so we can use them to predict the reactivity of elements, and they're also going to help us when we start looking at ions. So Bohr models, like I said, are used to predict reactivity of elements because they're going to show how the electrons are arranged in that atom. And those electrons have everything to do with how the element reacts. And when we talk about reactivity, we refer to how likely that element is to form a compound with another element. So this is going to be really useful when we get into bonding in the next chapter. When we're looking at Bohr models, we're going to look at the valence electrons, which are the electrons on that last energy level, and those will tell us how the element is going to react. So the way that we're going to do them is we're going to draw the nucleus. We're just going to draw a circle in the middle, and we're going to write the number of neutrons and protons in that nucleus. I'm not going to have you draw them all out. That seems a little redundant, but we're just going to write the number of protons and neutrons in the nucleus. Then we're going to write out the electron configuration, and we're going to use that electron configuration to draw the appropriate number of energy levels, and then we're going to use that electron configuration to put the electrons in their appropriate energy levels, and then we can see how many electrons are in that outermost energy level, which is really what we're looking at. So let's try this out. So we have carbon. Carbon is atomic number 6, which means that it has 6 protons, and it also has, since it's neutral, right, it's also going to have 6 electrons because the protons and the electrons need to be equal in a neutral atom. And you'll recall the way that we find out the neutrons is we do mass minus protons, right? That 12 is our atomic mass, but we need to get the mass number, so we round it to a whole number, and that will give us 12, and then mass minus protons, or mass minus the atomic number, will give us the number of neutrons. Then we can go through and write out the electron configuration. So we'll find carbon on our periodic table, that's here, and then we'll go through, again, starting at the top left, and we'll write the electron configuration. So we're going to get, right, carbon's not in the 1s, so we will get 1s2, carbon's not in the 2s, so we'll get 2s2, but carbon is in the 2p, it's at the second one in the 2p, so we write 2p2. So now it asks, how many energy levels will this have? So to figure out the energy levels, we're going to look at the principal quantum number, which is the number in the front. So we're looking at 1 versus 2 versus 2. So we're going to find the largest number in the front. That will tell us how many energy levels that this has. So the largest number in the front of any of those is a 2. Okay, so it's going to have 2 energy levels. So now, before we answer this next one here about the valence electrons, we're going to go ahead and draw the Bohr model. So we'll draw a circle in the middle that will count as our nucleus. And we're going to put our number of protons and neutrons. So we have P+, that's our abbreviation for protons. There are 6 protons, and our neutrons in 0, we have 6 neutrons. And then it says we have 2 energy levels, right? The largest number in the front is a 2. So we're going to draw 2 circles around our nucleus. And I'm sorry, I'm not very good at drawing perfect circles. Now we're going to fill in our electrons. Okay, so we're going to use the electron configuration to do this. So this 2 right here, this tells us a number of electrons. So this tells us there are 2 electrons in the first energy level. So we're going to put 2 electrons on the first energy level, and you can put them wherever you like. And then the next one there tells us there are 2 electrons in the second energy level. So we'll put 2 electrons in the second energy level. And this 2 tells us there's another 2 electrons in the second energy level. So we'll put 2 more electrons in the second energy level. Okay, so the superscripts are telling us a number of electrons, and we can look at the principal quantum number, right, to tell us in, which energy level it is. So we have 2 electrons in the second energy level plus another 2 electrons in the second energy level, and there were 2 electrons in the first energy level. Okay, so now it asks how many valence or outer electrons does this element have? So we're going to look at the outermost energy level, which is the second one, right? This was principal quantum number 1, this was 2. So we're going to look at the outermost energy level, and we're seeing that we have 4. We have 1, 2, 3, 4 electrons in the outermost energy level. That means that carbon has 4 valence electrons. Let's try another. So now we're going to do this for arsenic. Arsenic is atomic number 33, which means that it has 33 protons, and since protons and electrons have to be equal when in a neutral atom, we will also have 33 electrons. Now to find the neutrons, we need to have the mass number, so we do 74.992 rounded to 75, right? That gets our mass number. And then our neutrons will be our mass minus our protons. That will get us our number of neutrons. Then we can write out the electron configuration for arsenic. So arsenic's down here. So arsenic is not in the 1s, so we write down 1s2. It's not in the 2s, so we write down 2s2. Not in the 2p, so we have 2p6. Not in the 3s, so 3s2. Not in the 3p, so we have 3p6. Not in the 4s, so 4s2. And then remember, the D block is numbered differently. This is 3, 4, 5, 6. So this is 3D. And it's not in the 3D, so we have 3D10. And then it is in the 4p, so we have 4p, 1, 2, 3. So then when it's asking how many energy levels will this have, we're going to look for the largest number in front. So the largest number that comes before a letter. And you'll see the largest number is going to be a 4. We have 4 twice there, so this will have 4 energy levels. Now we can go through and draw the Bohr model. So again, we're going to draw a circle for the nucleus. We'll write our number of protons and our number of neutrons. And then we're going to draw 4 energy levels. So now we have 2 electrons that are going on the first energy level. We have 2 electrons that are going on the second energy level. Oops, sorry, not there. And then we have another 6 electrons that are going on the second energy level. So we have 1, 2, 3, 4, 5, 6. Then we have 2 electrons that are going on the third energy level. Then we have 6 more electrons that are going on the third energy level. We have 2 electrons that are going on the fourth energy level. And then we have 10 electrons that are going back on the third energy level. So we have 10 more for the third. And then we have 3 electrons that are going on the fourth energy level. So now when it asks how many valence or outer electrons this element has, we count the ones on the outermost, which is that fourth energy level. So we'll see it has 1, 2, 3, 4, 5 electrons on the outermost energy level, which means that it has 5 valence electrons. So the valence electrons, if you'll notice, are always the one in the S and P sublevels for the highest energy level. And they're actually going to be related to the group number. So if you look, when we had our valence electrons for arsenic, right, we had our fourth energy level, that's these 2, right, that 2 electrons here, 2 electrons in the 4s, and 3 electrons in the 4p, gave us our 5 valence electrons. So they're always going to be the total number of electrons that the element has in the s and p orbitals together. Okay, and they're related to the group number of the element. So if we look, right, this was 1a, 2a, 3a, 4a, 5a, right? And since arsenic is in 5a, it had 5 valence electrons. So like something else that would be in, 3A would have 3 valence electrons. If it was in 8A, it has 8 valence electrons, except for helium. But so they're always going to be related to the group number here. And we're only going to do this for ones that are in the S block or the P block, not the D block elements. But this valence electrons are really important because they determine the chemical properties of the element. And they're going to determine how this element reacts with other elements. So this is going to be really important when we get to bonding. So like I said, if we have elements in group 2A, they will have 2 valence electrons, and they will all do this, because they're all going to end in S2. So if we look at the periodic table, all of these, like beryllium, would end in 2s2. Magnesium would end in 3s2. Calcium would end in 4s2. So they're all going to have 2 electrons in their outermost energy levels. They will all have 2 valence electrons. So that group number along the top tells us the number of valence electrons that the element has. Like I told you, the periodic table is like the world's greatest cheat sheet. Right? So if we can just look at the group number along the top or count the group number, then you can figure out how many valence electrons something has, and that tells you so much about the reactivity of the element. Okay, go ahead and pause here and complete problems number 17 through 21 to do some work on Bohr models and valence electrons. Okay, Lewis dot symbols are really useful, again, when we get to bonding. They're going to show us the number of valence electrons as dots around the element. So like magnesium, if we wrote out the electron configuration for magnesium, right, 1s2, 2s2, 2p6, 3s2, this 3s2, right, there are 2 electrons in the 3rd energy level, which is the outermost energy level. So magnesium has 2 valence electrons. So the way that we draw these Lewis dot symbols is we draw the element symbol, so Mg, and then we put 2 dots around magnesium. Okay, and so these are all the different ways you could show that magnesium has 2 valence electrons. The important thing here is to think about magnesium, right, our element symbol, think about it being in a box. And you can put, electrons on the sides of the box, but you can't put it on the corners of the box. You can't put it here. You can only put it on the sides of the box, and you can't put these electrons together because the electrons aren't paired. These are unpaired electrons, which makes a really big difference in chemistry. So usually when we draw these, we're going to put electrons, we'll put 1 on each side of the box before any get 2. Kind of like when we were doing our orbital diagrams, we had to put 1 electron in each orbital before any got 2. It's the same kind of thing here. We're going to put 1 electron in each on each side of the box before any get 2. Okay, so we're always going to determine how many valence electrons an atom has and then space them around the element symbol. So if we look at oxygen, oxygen is in group 6A. Okay, and that tells us that oxygen is going to have 6 valence electrons. So we're going to start, this is my helpful hint to you. Start by putting 1 electron on each side and then continuing around clockwise. So like we would put 1, 2, 3, 4, 5, 6. And the reason for this, and this is really important in higher levels of chem, these are called paired electrons, right? Where they have, they have 2 on one side of, our box that we've put our element symbol in. So those are paired electrons, and it's important for oxygen that the paired electrons end up next to each other when we get into bonding. Okay, so we want to put them around in a circle. We don't want to just put them and be like, here's some electrons. Because if you end up with the paired electrons across from each other like this, that's actually going to tell you things incorrectly about bonding. So anything, this is just for group 6A actually, that is really particular, but you need to end up with your paired electrons next to each other. Okay, now let's look at fluorine. Fluorine is in group 7A, so we have 7 valence electrons, so we go 1, 2, 3, 4, 5, 6, 7. Nitrogen is in group 5A, so it has 5 valence electrons, so we go 1, 2, 3, 4, 5. Now, you'll notice that it doesn't matter where I start, right? If I start on the bottom or the top or on the left, it doesn't matter where I start putting electrons. Is always You need to put 1 electron on each side before any get 2. So like I was kind of alluding to, when we have electrons, when we have 2 of them on the same side, we call them paired electrons, or you'll also hear them sometimes called lone pairs. And lone pairs and paired electrons are not going to be involved in bonding. They are, lonely. They hang out by themselves. They're not going to be involved in bonding. So it's important to separate which ones are paired and which ones are unpaired. Unpaired electrons are electrons that are available to participate in bonding. So chlorine has 1 unpaired electron, so it can make 1 bond. Carbon has 4 unpaired electrons, so carbon can make 4 bonds, which gives carbon a lot of really cool properties, which is why carbon is used in so many different compounds. So here's, if we're looking just kind of on a periodic table, our number of valence electrons. So we have our group numbers up here. All of the A's, we're skipping the D block, 1A, 2A, 3A, etc. And you'll notice that corresponds to the number of valence electrons. So, something in group 5A has 5 valence electrons. And that's what we're seeing here. Then they would all have 5 dots around that element. Okay, so our group number tells us our number of valence electrons. Go ahead and complete problem number 22 on your lecture worksheet. And once you're done, go ahead and come back. Okay, we're going to talk now a little bit about other trends that we can see on our periodic table. Okay, more reasons why our periodic table tells us all the information that we need to know about chemistry. Another thing that we can see is atomic size. Okay, and sometimes you'll hear this called the atomic radius. They mean the same thing essentially. We're just trying to get a measure of how big our atom is. Okay, so our atomic size is determined by the distance of the valence electrons from the nucleus. Right, so it's the distance from, the inside out. So that's why we also call it the atomic radius, because it's like the radius of a circle. So as we go, down the period like this, as we go down the periodic table, you would, the atoms are getting more protons, they're getting more neutrons, they're getting more electrons. So it makes sense that that atomic size increases. We're adding more and more electrons into bigger and bigger energy levels, right? Energy levels that are farther and farther away from the nucleus. So it makes sense that our atom is getting larger and larger and larger. The one that's weird, and it's the one periodic trend that you'll notice is kind of backwards from what you might think, is this arrow. You'll notice that it says the atomic size decreases as we go that way. So as we're going to the right, our atom is getting smaller, and you can see that based on these images, right? Our atom is getting smaller as we go to the right. But you may be thinking, hang on, well, that doesn't quite make sense, because as we go to the right, we're increasing the number of protons, we are increasing the number of neutrons, we are increasing the number of electrons, so our atom should get bigger, right? We're having more stuff. Why is it not getting bigger? And you're right. Logically you would think, okay, well, it should get bigger, but it doesn't. And the reason that it doesn't get bigger is because as we're going to the right, you're correct. We're adding more protons and we're adding more neutrons. Those are all going in the nucleus. Those aren't really changing the size of the atom all that much because they're going in the middle. What really determines the size of our atom is our electrons. And we're adding on, as we go, to the right, we're not adding on more energy levels. We're adding more electrons to the same energy level. So if we think about, I'm going to draw, this is my nucleus for now. And let's say we're looking at beryllium. Beryllium has 2 electrons in the first energy level, and it has 2 electrons in the second energy level. Well, as we go to the right on the periodic table, right, we start adding more electrons to that same energy level. We're still adding electrons to the same energy level because this is the 2s, and this is the 2p. So we're adding, another electron here to boron, and then this would be carbon, and then nitrogen, and oxygen, and fluorine, and neon. And as we add more electrons to that same energy level, this energy level becomes more negatively charged, essentially, and we're adding more protons to our nucleus, so our nucleus is becoming more positively charged. So as we add more protons to the same place and more electrons to the same place, we're increasing the electrical charge, which means we're increasing the attraction between the second energy level and the nucleus. So when we do that, you can think about them being like bigger and bigger magnets. We're putting, bigger magnets around the outside and bigger magnets in the middle, and that increases the attraction. And when it does that, it draws that second energy level in closer to the nucleus, and it's actually making the atom smaller. Because so there's more protons in the nucleus, more electrons in the same energy level, that draws that second energy level in closer and closer and closer to the nucleus, making the atom smaller and smaller and smaller as we go to the right. So that's what's happening. So I would make yourself a note somewhere. This is the one periodic trend that tends to trip people up, because they think, as we add more protons and more electrons, it should get bigger. But it doesn't, because we're adding more protons to the same place, more electrons to the same energy level. Again, think of them like bigger and bigger magnets. It's going to draw it in closer and make it smaller. So in the second period, neon is the smallest one and lithium is the biggest one, even though neon has a lot more protons, neutrons, and electrons. So again, I would make a note of this. So again, atomic radius is half the distance across an atom, and the atomic radius decreases as you travel to the right. So it's getting smaller as you travel to the right, because the number of protons is increasing. This draws the electrons in closer, which makes the atom smaller. Okay, so on that periodic table that we keep making notes on, right, that one that was blank that we've colored, and we've written the SPDF blocks, I would also make yourself notes about the increasing atomic radius. So it gets bigger, right, going to the left and down. So that means that francium is the largest atom on the periodic table, and helium is the smallest. So our periodic trend for radius, AR, goes that way. Okay, it increases going to the left and down. Go ahead, complete lecture worksheet problem number 23 on atomic radius. Okay, our next trend that we're going to talk about is ionization energy. And ionization energy has to do with bonding, so it's really useful for us to talk about. So ionization energy is the energy it takes to remove a valence electron. So if we think about sodium, sodium has an electron configuration of 1s2, 2s2, 2p6, and 3s1. Okay, so this is an orbital diagram, just kind of laid out, left to right instead of up and down. So if we think about, sodium, how do we get to sodium, which is Na+? Okay, so what we need to do, Na+ is telling us that it has more protons than it has electrons. Na+ tells us it has lost an electron. We've removed an electron. Okay, so what's happening is we are removing the valence electron. We are taking away the electron in the outermost energy level. And so now, right, sodium normally has 11 electrons, but if we take this one away, now it only has 10 electrons, but it still has 11 protons, right? We didn't change the number of protons. We only changed the number of electrons. We cannot change the number of protons, because if we change the number of protons, then we change which atom it is. Like if we took away a proton, now it becomes neon instead of sodium. Okay, so we can't change the number of protons, but you can change the number of electrons, and this makes ions, which we will get more into in the next chapter. But when we remove this valence electron here, now we don't have the same number of protons and electrons. We have one extra proton, so that's why we call it Na+. So when we've pulled this electron off, we make a positively charged ion. Okay, so the ionization energy is the energy it takes to pull off that valence electron. Okay, the energy required to remove a valence electron from an atom. If an atom, and this is just like the wording, if an atom has really high ionization energy, that means it's hard to remove the electron. You can think about it as being like a cost, right? If it has a high ionization energy, it has a high energy cost to pull that electron off. Okay, it means that those electrons are being held really tightly to the nucleus. Okay, they're really attracted to those protons in the nucleus. And this high ionization energy happens as the electron, or as the atom gets smaller. The closer those valence electrons are to the nucleus, the more tightly they are being held to the nucleus. So that's why helium, our smallest atom, is going to have our highest ionization energy, because those electrons are being held really closely to the nucleus. Francium, our largest atom, will have the lowest ionization energy because those electrons, those outermost electrons, are really far away from the nucleus. So it can't hold on to those electrons so tightly. Okay, so our ionization energy increases going to the right and up. So the smallest atoms will have the highest ionization energy, and the largest atoms will have the lowest ionization energy. Again, think of the term ionization energy as like an energy cost to remove that valence electron. So again, I would make notes of this on that blank periodic table. You can abbreviate ionization energy as IE. Metals have 1 to 3 valence electrons, and they're larger, right? Our metals are on the left side of our periodic table. They are always going to be larger than our nonmetals, which are on the right side of the periodic table. So metals with only 1 to 3 valence electrons are really large, and they have very low ionization energies. Nonmetals have more valence electrons, right? 5 to 7 valence electrons. They have really high ionization energies because they are smaller. Noble gases have complete octets, and octets is going to be super important when we get to bonding. And what we mean by an octet is that it has 8 valence electrons, and you'll see when we get to bonding that 8 valence electrons is the goal. Okay, we're always trying to get to 8 valence electrons, except for helium and hydrogen, which are trying to get to 2. We still call it an octet though, just mostly. You'll sometimes heard it called a duet. But that means that they have a complete outer energy level. They have 8 valence electrons. And since the goal in bonding is to always get to 8 valence electrons, and noble gases already have 8, they have extremely high ionization energies because they already have 8 valence electrons. So they're not trying to lose any, right? They don't want to lose any valence electrons because, like I said, the goal of bonding is to get to 8. So metals are very large atoms, so they have very low ionization energies. Nonmetals are smaller atoms, so they have higher ionization energies. And noble gases are the smallest atoms, and they already have 8 valence electrons, so they have extremely high ionization energies. Okay, go ahead and complete problem number 24 on your lecture worksheet. Our last periodic trend that we're going to talk about today is electronegativity. And electronegativity is the ability of an element to attract electrons. And this is going to be mostly when we're talking about molecular bonding and forming covalent bonds. And it's going to be the ability of an element to shift electrons in a molecule. Fluorine is the most electronegative atom. So that's fluorine here. And you'll notice that it's not in the corners. Mostly we've been talking about francium and helium, but now I'm telling you fluorine is the most electronegative atom. And the reason for this is that noble gases do not have an electronegativity value. So these guys, these noble gases, we're not going to include them when we're talking about electronegativity. They have an electronegativity value of 0. They are inert, they are unreactive. The noble gases don't form compounds because they already have 8 valence electrons. Okay, the whole point of bonding is to get 8 valence electrons. You're going to give your electrons away, you're going to gain some new ones, you're going to share electrons, but it's all so that those elements can get 8 valence electrons. Since our noble gases already have 8 valence electrons, they don't want any electrons. They're not trying to lose electrons, they're not trying to gain electrons, they don't even want to share them. They are not going to form bonds. So our noble gases have an electronegativity value of 0 because they aren't, forming bonds. They are inert, they're unreactive, they're not going to gain or lose electrons. So we're not going to look at them for this section on electronegativity, which means that fluorine now is our highest electronegativity value. And our electronegativity value has the same trend. It's going to increase going to the right and up, so the smaller atoms are going to have higher electronegativities, and the larger atoms are going to have lower electronegativities. This is the same as the trend in our ionization energies. It's the same because smaller atoms are better able, right, their protons are kind of closer to the outside of their atom, and they're better able to have a pull on electrons. Okay, so the larger atoms like francium If we think the distance from, the center of francium, right, the nucleus of francium, to its outermost electrons, those are really far away. So it's not going to be able to, gain or, shift any electrons that are really, really far out there, right, in a bond. If we're thinking about francium being bonded to something, those protons aren't going to have much of an effect on the electrons in that outermost energy level because it's so big. So again, the smaller the atom is, the more those protons will have an effect on the outermost electrons. Okay, go ahead and complete lecture worksheet problem number 25. So again, you'll notice that electronegativity and ionization energy have similar trends, right? Not exactly the same because we're not looking at the noble gases for electronegativity, but it's the same general direction. And the reason for this is that atoms that really want an electron, right? Atoms that are trying to pull electrons toward the atom, that means they have a high electronegativity. The higher that electronegativity, right, the more they're trying to get electrons, the less willing they are to give up their electrons. Okay, the better able that they are to pull those electrons toward the nucleus means that they are being held more tightly to the nucleus, which means it's going to cause a higher ionization energy. So they're not going to be able to give up their electrons that easily. Okay, so electronegativity and ionization energy have a similar trend, and again, this is mostly going to be based on the atom's size, because the smaller that atom is, the better able those protons are able to hold on to those valence electrons. Let's try this out. Let's get some practice. So if you have a periodic table near you, go ahead and find potassium and bromine and boron and indium. And I want you to go ahead and pause here and figure out which one of those in each pair has the larger atomic radius, electronegativity, and ionization energy. And then once you're ready, unpause and I'll give you the answer. Okay, so if we look at potassium versus bromine, potassium and bromine are in the same period. So we have potassium on the left and we'll have bromine on the right. So if we think about our trends, then when we're looking at atomic radius, remember atomic radius gets bigger going this way, right? Going to the left. So that means that potassium has a larger atomic radius. If we think about ionization energy, that's going to increase going to the right, and so will electronegativity. So that means that bromine has a higher electronegativity and a higher ionization energy, because remember, they have similar trends. If we think about, if we think about boron and indium are stacked up and down. Okay, so atomic radius increases going down the periodic table. So that means that indium will have a larger atomic radius. We think about ionization energy and electronegativity, both of those increase going up the periodic table. So that means that boron will have a higher electronegativity and a higher ionization energy. Okay, so we're looking at trends here. So you need to have these trends memorized for your next quiz and the exam on this information. Okay, you're not going to be able to use this cheat sheet that we've been building, but like I said, the periodic table is your greatest cheat sheet ever. It has all of this information in there. You just need to remember some trends that go along with it.